Hi, hello everyone, welcome back. My name is Attila Berets. This is our second video in our solar energy course. I hope you will enjoy it. In the first video, I was talking about the structure, age, and the operation of the sun. In this one, we will learn about the sunshine traveling through the deep space, our atmosphere, and only a part of it arriving on the surface of the Earth. So let's see, what will I exactly talking about? First of all, the origin and the properties of the sunlight. After that, the factors determining the amount of incoming light. And on the end of the video, I will talk about some of the measuring equipment as well. Do you remember this side of the previous video? As we discussed before, the sun is a huge hot gas ball. We should quickly review some layers of the sun. First of all, we should talk about the core. In its core, there is a nuclear reaction where hydrogen is burned to helium. During this process, a huge amount of energy is produced. You can see the chemical equation. On the left side, the input, 4 protons and 4 electrons, actually 4 hydrogen atoms, and on the right side, on the output, the helium with 4 protons and only 2 electrons. It means we have 2 electrons less on the right side. According to the law of the physics, the mass became energy. It has 2 forms, motion energy and gamma rays. So this is where the energy is originated from. We should mention the photosphere as well. This is actually the visible surface of the sun. This is the first layer of the sun atmosphere, which is the tiniest actually, only a few hundred kilometers thick. Here is the temperature dramatically decreases to about 6,000 Kelvin. It is important in this video because the energy is produced in our star is radiated from this layer in the form of the light. The chromosphere is the middle layer of the sun atmosphere. Here the temperature increases to about 10,000 Kelvin. This is the layer which radiates most of the sun harmful ultraviolet waves. So the energy is developing in the core of the sun and it is radiated to the deep space from the photosphere and from the chromosphere. So we know already where the light is coming from. Now let's see its properties. The light or energy, actually the whole solar system is an electromagnetic radiation. As you see on the picture, the energy propagates in the form of waves. The sunlight represents the entire electromagnetic radiation. What we call visible light is a small portion of the electromagnetic spectrum, actually here, this area. And all the different colors are electromagnetic waves with different wavelengths. We will talk about it soon. Electromagnetic spectrum is a range of all types of electromagnetic radiation based on the wavelength. Wavelength is a distance between the bumps of the waves. The frequency, which is also an important feature of the waves here, is the number of occurrences of repeating event per unit of time. Actually, how many ups and downs are happening in 1 minute. The lower the frequency, the longer the wavelength and vice versa. This inverse relationship can be seen on the left side. In this direction, the wavelength, and the other direction, the frequency is increasing. And with the frequency, the energy is increasing as well. So gamma rays has much bigger energy than the radio waves actually. You can see the size of the wavelength. A radio frequency has a wavelength as big as a building. The visible light is a bacteria size, more or less, and the gamma rays on the right side, its wavelength is smaller than the atoms actually. As we discussed before, the visible light is only a part of the spectrum. We see it as a white light. But as you see, this is the visible spectrum. It is not white, but a mixture of different colors. So let's investigate its color a bit. As I said, it's not a single color, but it's a mixture of 7 colors of the rainbow. It is quite easy to see, just we need a prism. In the prism, because of the refraction, one, when the light enters, and the second, when it exits from the prism, the light splits up to its components. Or we can see it when it rains, but the sun still shining behind us, then we can see the rainbows. Here, we can see the 7 colors of the rainbow, the red, orange, yellow, green, blue, indigo, and violet. As you remember, the energy of it increases as its frequency is increasing. As we saw before, the white light can be split up to make separate colors, but it works in the other way as well. We can add the colors together, make a white color. The primary colors of light are the red, the blue, and the green. Mixing this color, we can make other colors. For example, mixing blue and red, we can make magenta. And if we mix blue and green, we can make cyan, actually light blue. Adding red and green makes yellow. And if we add all the 3 together again, we will get the white light again. We were talking about the colors, but how do we see them? The color of an object depends on the color of the light it reflects. When a white light strikes a red object, the red frequencies are reflected and the other frequencies are absorbed. All the 7 colors are incoming, 6 of them absorbing, and only the red light is reflected. The white object reflects all the frequencies, and black objects, like a black hole, absorb all frequencies. Now we've finished the first part of the video, so it's time for a quick quiz to check your knowledge. First of all, what color has the sun? I hope you remember that the sun is not a single color, the sunshine I mean, it's not a single color, not a white light, but it's a mixture of the 7 colors of the rainbow. The second question is, which part of the electromagnetic spectrum has the longer wavelength? Infrared or ultraviolet? I could ask also, which is the less dangerous? Actually, this is the infrared with longer wavelength. That's why it is less dangerous. The third and the last question, what are the 7 colors of the rainbow? These are the red, orange, yellow, green, blue, indigo, and violet. In the second part of the video, I will talk about the factors determining the amount of incoming light. The sunshine is starting its long way from the sun to the earth. It takes about 8 minutes and 17 seconds to travel the average distance from the surface of the sun to the earth. Actually, the average distance is 150 million kilometers. And as you see, the maximum distance is 152 million kilometers, occurs at summer solstice, and the minimum distance is 147 million kilometers, occurs at winter solstice. As you see, the summer solstice is when the sun reaches its highest position in the sky, and the day is the longest. Each day has the shortest night and the longest daylight. When it happens, it depends on the calendar, but in between June 20 and 22, in the northern hemisphere and between 20th of December and the 23rd of December in the south hemisphere. As you see, the light has a really fast speed. This speed, that's 300 kilometers per second, means only in deep space. When the sun reaches the atmosphere or enters in any materials, it slows down. On this slide, you can see the proportion of the sun and the earth. If we assume that the earth is a normal sized globus, here on the right side, what actually everybody knows from the geography lessons, the sun is a 10-story building with 33 meters height in the distance of 3.5 kilometers away. So we know already that the sunshine is radiated from the surface of the sun and it travels with a great speed in the deep space. But the energy it carries decreases as it travels further away from the sun. As you see, the amount of energy spreads on a bigger surface as it travels further. Here, you can see the planets in a row according its distances from the sun. I highlighted Earth. We were discussed that its average distance is 150 million kilometers. It gets 1,367 watts per square meter energy on the surface of its atmosphere. Mercury is much closer to the sun, so it gets much more energy. Therefore, it is really hot. But the big ice planets here are much further, so they are much colder because they get much less energy. This approximately 1,367 watts per square meter, what reaches the outer perimeter of the Earth's atmosphere, is the so-called solar constant. This means that if our solar panel could be installed outside the atmosphere, in the outer space, and always rotated towards to the sun, the surface of the collector would be continuously exposed to this powerful solar radiation. For solar energy calculations, it is a really important measure. You can see also that this energy is not reaches the surface of the Earth, luckily, because it would be really hot. As it travels through the atmosphere, it loses some of this energy, and a maximum 1,000 watt per square meter reaches the surface. The atmosphere causes a constant, predictable attenuation of solar radiation reaching the Earth's surface. Let's see what are the causes of the energy loss. These are the reflection, the absorption, and scattering. First of all, the reflection, which is the change in a direction of a wavefront at an interface between two different media, so that the wavefront returns into the medium from which it originated. Or just simply look into the mirror and you see your reflection. When the light reaches the atmosphere, some of part is reflected back to the space, the remaining part is moving further, but when it meets with the clouds, some of it reflects from the top of the clouds, and depending on the surface, what it hits, some of it will be reflected by the surface. It is called albedo. We will talk about it later. These photographs below show how the light is reflected on a still lake, creating a mirror image. The still flat surface of the lake has acted as a mirror. Most surfaces reflect light. Let's look at how this happens. The ray which hits the surface is called the incident ray. The ray which is reflected from the surface is called the reflected ray. When we draw diagrams of reflection, we also draw an imaginary line to help us measure different angles. This line is called the normal. The normal line is always drawn perpendicular to the surface. Between the normal line and the incident ray, there are two angles. These are the angle of incident, the angle between the incident ray and the normal line, and the angle of reflection, the angle between the reflected ray and the normal line. Absorption. When light hits a surface, some of the light is absorbed and the rest is reflected. It is the reflected light that reaches our eyes and allows us to see the object. Previously, we learned that white light is a mixture of different colors. When white light from the sun hits the leaf here, all the colors are absorbed except green. So green light is reflected back to our eyes, and so we see the green leaf. Absorption has a notable effect. Attenuation is to gradually reduce the intensity of the light waves as they propagate through a medium. The main absorber is the ground. It takes a lot of heat and it will heat up the air above it. But as you see, the atmosphere, especially when it is dirty, contains a lot of dirt and vapor, absorbs a big amount of energy as the clouds does. Different molecules absorb sunlight at certain wavelengths. For example, water vapor and carbon dioxide absorb sunlight in the visible and infrared region. But ozone absorbs sunlight in the UV region. We learned that UV is quite dangerous. Therefore, we should protect our ozone layer. Particles in the atmosphere which are exposed to light absorb light energy and re-emit light in a different direction with a different intensity. Blue light has a wavelength similar to the size of the particles in the atmosphere. Therefore, blue light scatters. That's why we see the blue sky. The higher we climb in an aircraft, the less air particles are present. Therefore, the scattering is less, so the color of the sky changes from blue slowly to black. Red light has a wavelength that is larger than most particles. That's why it is unaffected, traveling through the atmosphere easily. Albedo, in general, is a measure of the ability of electromagnetic rays to reflect on the surface. Albedo is most often examined in a visible wavelength range. On this slide, you can see the different areas, different albedo values. As you see, the higher the albedo, the more light is reflected. So actually a mirror would be the winner in this game. The Earth average albedo is 31%. Fresh snow reflects a lot of light. Albedo is 80–90%. The grass area 20–30%, and forest actually just around 10–20% of the light reflecting. The largest albedo currently known is that one of the Saturn moons, Enceladus, 99% of the albedo. It means almost 100 of the light is reflected from the surface of it. And the lowest, of course, the black holes, which takes all the light and reflecting nothing at all. Just a quick review about the main radiation types. Scattered sunlight, what makes the sky blue, it is responsible for the light entering the north-facing windows on the north hemisphere. It is referred to as a diffuse radiation. The second one is the direct or beam radiations, sunlight that reaches the Earth's surface without scattering. Sunlight that is reflected from the ground is called albedo radiation, as we were talking about it, and the sum of the three components above is called the global radiation. Every point on the Earth gets sunlight for at least a part of a year. The amount of solar radiation reaching any point of the Earth's surface depends on, first of all, the geographical position, the season, the relief, in other terms, the angle of incidence of the sunshine, and the light transmittance of the air, the clouds, and atmospheric conditions. Because of this, on a spot on the Earth, we distinguish between possible, actual, and relative sunlight duration. For example, in Hungary, the possible sunlight duration every day from sunrise to sunset is around 2,000 hours per year, and the relative is 55%. Because of the polar axis is not vertical, the sun moves during the year between the Tropic of Cancer here and the Tropic of Capricorn here. These areas between the two get the much more energy, so these are the warm regions. As we travel north or to the south, actually, all the areas get less and less energy, so they are the colder areas. On this slide, you can see the average annual sunshine. You can see that because of its geographical position, Dublin, here is green, actually it is anyway green, is much less sunny than, for example, Rome. Season is a division of the year marked by changes in weather, ecology, and the amount of daylight. On Earth, seasons are the results of Earth's orbit around the Sun and the Earth's axial tilt relative to the ecliptic plane. In temperature and polar regions, the seasons are marked by changes in the intensity of sunlight that reaches the Earth's surface, variations of which may cause animals to undergo hibernation or to migrate, and the plants to be dormant. Various cultures define the number and nature of seasons based on regional variations. So why we have seasons? The polar axis of the Earth is inclined by an angle, as you see here, 23.45 degrees to the plane of the Earth's orbit. Okay. Look this situation. The southern hemisphere here faces towards to the sun. So here in Europe, we have winter, and here on the southern hemisphere, that is summer. During the year, the Earth is rotating around the sun. Half year later, the Earth is on the other side of its elliptic plane, so the sunshine is coming from the other side. On this slide, we see the situation at summer solstice. Here, the north hemisphere faces towards the sun, therefore we get the more heat, so we have summer here. And on the south hemisphere, there is winter. On this slide, we can see the half time between the two endpoints. At the two equinoxes, we have spring or autumn. This year, equinox was in March, 20th of March, and it will be the 22nd of September. What do you see on this slide? One of the reasons I would not live on the Arctic at all. At winter, the North Arctic area here is completely dark because the sunshine is not reaches it. If you see the first picture, if you sit on the top of the North Pole, you don't see the sun during the winter months, actually for half a year. On the second picture, when it is summer on the North Pole, the sun is all the time above the horizon, so there are 24 hours sunshine here. In temperate and subpolar regions, 4 seasons based on the Gregorian calendar are spring, summer, autumn or fall, and winter. Ecologists often use a 6 seasons model for temperate climate regions, which are not tied to any fixed calendar dates. Prevernal, vernal, estival, serotinal, autumnal, and hibernal. Many tropical regions have only 2 seasons, the rainy or monsoon season and the dry season. We distinguish the meteorological and astronomical seasons. First, let's see the meteorological seasons. Here the seasons are reckoned by temperature, with summer being the hottest quarter of the year and winter the coldest quarter of the year. You can see that in Europe, the winter, and in Australia, the summer starts the 1st of December. Astronomical seasons. Here the precise timing of seasons is determined by the exact times of transit of the Sun over the tropics of Cancer and the tropics of Capricorn. These are actually the solstices. And the times of the Sun transit over the equator, these are equinoxes. When we stay by the previous example, according to the astronomical seasons, in Europe, the winter, and in Australia, the summer, starts not the 1st of December, as with the meteorological season, but the 21st of December. When you plan your own solar sets, you should know the exact path of the Sun during the day. During the equinoxes, the Sun rises directly from the east and sets directly to the west in every place on the Earth. Apart from these days, the Sun rises southeast and sets southwest a bit. We know already some of the reasons why the amount of solar energy is different at any point of the Earth's surface. We were talking about the geographical position and the season, so let's see the relief. As you see on the flat plane, in the morning, the sunshine has a low angle of attack, but at the same time, still in the morning, on an eastern slope, it has a bigger angle of attack, which means an eastern slope warms up much faster. But it's also true that the same slope at the afternoon has a disadvantage. Because of it gets less energy. So the best wine regions at the northern hemisphere are on the southern slope. On the northern slope is much less or no sunshine at all. On the southern hemisphere is everything is the opposite of this. The relief is really important when you consider the tilt angle of a solar panel. Of course, with the mechanism, you can easily construct a southern slope on a flat plane as well. When you want a solar panel to heat up your swimming pool, so you need the bigger energy at summer, you should make a more flat tilt angle because summertime the sun is high on the sky. In case you need the max capacity of your solar set wintertime, when the sun is much lower, you should tilt the panel much more. Actually, the best if you can change the tilt angle during the year. Clouds are also an important factor determining the incoming energy. Do you remember 1,367 watt per square meter power arriving on the atmosphere, but maximum 1,000 watt per square meter reaches the ground? It is also only at noon when the weather is completely clear and there are no clouds in the sky. If the weather is overcast and cloudy, this will of course further weakening. In case of thin sporadic clouds, the value of solar radiation decreases to 700 to 800 watts per square meter. In the case of more extensive clouds, it is only 500 to 600 watts per square meter. And in case of dense dark cloud cover, it decreases to only 100 watts per square meter. But not only clouds, but sandstorm, smoke, vapor also have the same effect. The last thing determining the incoming energy I will talk about is atmospheric condition or air mass. At noon, looking in the sun is not the best idea, but when it is sunrise or sunset, you can do it. But why is it? We see already that the atmosphere absorbs, scatters a part of the light. The thicker the atmosphere, its filtering effect is greater. As you see, at noon, there is only 800 kilometers atmosphere above us, but at sunrise and sunset, the distance increases to 38 times of this. This distance is much bigger than this distance. And this thick air mass filters the light, especially when it contains vapor and dirt particles. And because we learned about the red light is not affected by scattering as much as the blue light, the thicker the air mass, the more red is the sunset or sunrise. We finished this part of the video, so it's time for a quick quiz. The first question, how long does it take for sunlight to reach the Earth? Do you remember? It takes about 8 minutes and 17 seconds to travel the average distance from the surface of the Sun to the Earth, which is 150 million kilometers. The second question, what losses reach the incoming sunlight? The reflection, the absorption, and scattering. The last question, what are the factors determining the amount of incoming light we were talking about in the last few minutes? The geographical location, the season, the relief, clouds, atmospheric conditions, and altitude. In this third part of the video, we will see some devices which are commonly used by meteorologists, researchers, to measure the different parameters of the sunlight. Which parameters we are measuring? We are measuring the radiation power, which is the watt per square meter, the duration, hours per day, and illuminance, the lux measure. Here below, we can see the instruments for these measurements. These are the pyranometer, which measures radiation power, the Campbell-Stokes sunlight meter, measures the duration of the sunlight, and selenium cell lux meter measures illuminance. So first, let's see the pyranometer, which is used for measuring the solar irradiance on a planar surface, and it's designed to measure the solar radiation flux density, watt per square meter. It measures the direct radiation and the diffuse radiation as well. As you see here, it has a glass dome. It is designed to have a 180 degrees field view, and it is functioning as an insulator as well. The second equipment is the Campbell-Stokes sunshine recorder. It is used to measure the sunny hours during the day when there was sunshine. Its construction, it has a 10 centimeters diameter transparent glass sphere mounted on a heavy base, a ball provided below the glass sphere, we don't see it really much, and the group is provided, insert the paper. Why it is working? The hours of bright sunshine are recorded by the rays of the sun passing through the sphere here, and the sunshine is traveling through this sphere. And because of the focus, it will make a burn hole on the paper, which is placed behind the glass sphere. The card itself is calibrated so that the hours and the minutes of the day can be seen easily on it. At dawn and dusk, however, the sun will usually leave only a scorch mark rather than a burn, so the readings at those times of the day are not so easy. Here, you can see 3 different cards. Summer cards are much longer than winter cards because summertime the sun shines longer. Here on the summer card, we can see that this given day, the sunny hours were more than 12 hours. Here, the sun was rising around at 6 o'clock in the morning, and you can see this burn mark is coming to the other way of the card, and it finishes behind 18 hours or 6 hours in the evening. So it means the sun was shining more than 12 hours this day. The last measuring tool I will talk about is the selenium cell lux meters, which is measuring the intensity of light, actually the illumination. Actually, in its sensor, an electric current is building, which is proportional to the intensity of the incident light. And this current is measured with a galvanometer. On a picture here, you can see a photographer tool, but in the smartphones, with camera also has the same lux meter to determine the shutter speed. We finished our study about the sunshine. In the next video, one of my colleagues will explain you the role of the sun in the life of flora and fauna. I hope you enjoyed this video. Thanks for watching. Bye.